Well, thanks a lot, Andre, for the introduction. It's an honor and a pleasure to be able to present some of my PhD results in this talk. Everything I'm going to talk about is joint work with my supervisor, Emilia Friedman. So the talk will be partitioned into several parts. I'll start with the introduction and motivation. Then I'll talk about the essence of our constructive finite-dimensional observer-based control design. I'll speak about delayed and sample data implementation, and time permitting, I'll talk about essentially what is the next step in our research, some recent results on semilinear PDEs. So let's start with an introduction. For PDEs, it is well known that arbitrarily small delays can lead to instability of a system. For example, we can consider the following wave equation, where we introduce a non-negative delay denoted by h into the boundary condition. It can be easily verified in this case that for h equals 0, all solutions of this system will be eventually 0. However, if h is positive, even arbitrarily small, it can be shown that this system has unbounded solutions. So the presence of delays in PDEs is a challenging problem, on the one hand. On the second hand, it is also ubiquitous. For example, in network control systems where we have sensors, controllers, actuators, all exchanging data through a communication network. Now, such configurations come with really important benefits. For example, they allow for long distance estimation and control, but they come also with imperfections, such as variable sampling, delays, packet dropouts, etc. Now, in the context of network-based control of PDEs, it has a lot of important applications, just to name a few. In the case of chemical reactors, the treatment of air polluted areas, and deployment of multi-agent systems, as one can see in the picture here. So approaches, control strategies that are robust with respect to delays are in very high demand for such applications. Now, one such approach introduced in 2012 by Friedman and Brzezowski for the following semilinear heat equation is called the spatial decomposition. In this approach, the underlying idea is to take the spatial domain, namely the interval between 0 and L, and to partition it into subcells, which correspond to the partition X sub J. Then the authors consider point measurements carried out at the center of each subcell in discrete time, and static output feedback, sample data via zero-order Hall device that has the following form, again, discrete in time, where the functions b sub j, the shape functions appearing on the right-hand side, are just the indicator functions of the subcells. Now, this approach works and is robust, obviously, with respect to delays. However, it comes with one important drawback, and it is that many actuators covering almost all domain and similarly many sensors are required for this control strategy. So this raises a few challenges. First, what happens if we have only a limited number of sensors and actuators? And moreover, recall that in the PDE we consider distributed control. What happens if we are limited to point, in particular boundary control and measurement? Now, two important papers that kind of motivated us in my PhD work are the following. So in 2018, Karafilis and Kristich introduced sample data boundary control for the heat equation using the technique that I'm going to talk about, modal decomposition, for the case of state feedback. And in 2019, Selivanov and Friedman designed finite-dimensional boundary observers for the heat equation, again, via modal decomposition in the delayed and sample data regime. So these were the motivating works at the beginning of my PhD thesis. And our objective was to consider and investigate finite-dimensional output feedback using this technique of modal decomposition. In particular, what was crucial to us throughout our work was three criteria. The approach should be constructive, preferably someone without any knowledge in PDE should be able to implement the control strategy. And it should be explicit. In what sense? Well, we want all quantities of interest that I'm going to talk about in this presentation to be estimated explicitly. And this will be a recurring theme throughout my talk. So let us present the essence of our constructive finite-dimensional observer-based control. So in this 2020 Automatica paper, we considered the following reaction diffusion equation, where on the right-hand side, we have a Sturm-Liouville operator, and we have some key ingredients. So the functions P and Q satisfy these smoothness and these boundedness assumptions. We have a shape function that we denote by B, subject to these assumptions. And as you can see here, we consider non-local actuation or distributed control and boundary measurement carried out at the left boundary of the problem. For simplicity, throughout the entire talk, I'll focus on the case where P is equal to 1, Q is 0, and QC will just be denoted by Q. Everything I'm going to say here can be very easily extended to this more general framework of general Sturm-Liouville problems. So the initial point for a model decomposition is to consider this Sturm-Liouville problem over the interval 0, 1 with the following initial and boundary conditions. And it is well known that it induces a sequence of eigenvalues that I'll denote by lambda sub n that tend to infinity as n tends to infinity, and corresponding complete and orthonormal in L2 sequence of eigenfunctions. Now, for the particular case that I'm presenting here, these can be obtained explicitly and are given here. So the idea of model decomposition, essentially solution by separation of variables, is to take our solution and to represent it as a series expansion with respect to this eigenbasis. Now here, Zn is just the projection coefficient onto the nth eigenfunction. Then we can exchange our PDE with an infinite sequence of ordinary differential equations just by differentiating this projection coefficient, integrating by parts, and we obtain this sequence of ODEs. And in particular, what will be important in a few slides, note that these B sub n's here are just the projections of the shape function onto the eigenbasis. So in essence, the idea of model decomposition is to take the state, pass it through Fourier transform, and separate the modes or the frequencies into two parts. We will have a finite dimensional part that corresponds to finitely many, let's say, badly behaved or relatively unstable eigenvalues. And we will also have an infinite dimensional part of nicely behaved eigenvalues. Now, as I've mentioned already, this approach is not new. It was popular in the 80s, for example, in these two seminal works by Curtin and Ballas. But it's becoming popular again because of its robustness to sampling and delay and compatibility with input delay compensation. Again, two themes that I'll get back to shortly. So a few words, and this is by no means an exhaustive list, on finite dimensional observer-based control in the case of bounded control and observation operators. So in 82, Curtin, in a seminal paper, considered this problem, however, under restricted assumptions, namely that this shape function appearing on the right-hand side satisfies this condition. This essentially means that it is a superposition of finitely many eigenfunctions. In 88, Ballas gave a qualitative result. He said that, or showed that for a large enough, what he calls residual mode filter dimension, the closed loop system, obtained closed loop system will be stable. The first step towards a quantitative result was given by Haucourt and Deutscher in their 2011 IJC paper. However, their approach gives a rather conservative estimate on the dimension of the output filter, and also it's fairly difficult to compute. Now, for the case of delayed observer-based control, we have a paper in TAC in 21, where we considered a PDE observer. Now, in this case, when we have a PDE observer, the problem is simplified because it allows for separation of observer-controller designs. So in continuation to this work, which was the first paper of my PhD thesis, we set a goal of easily verifiable in efficient conditions for finite-dimensional observer-based controller, and this is what I'm going to present here. So just to recap, we have this infinite sequence of ordinary differential equations satisfied by the projection coefficients, and we proceed as follows. We take delta to be a desired decay rate, and we will introduce two parameters. So the first parameter, I'll denote it by n naught, will satisfy this inequality. Note that this inequality eventually holds because the eigenvalues tend to infinity. This n naught will be the controller dimension. We will also need another parameter, capital N, larger or equal to n naught, which will be the observer dimension. Then our finite dimensional observer is constructed as a superposition of the first n, capital N, eigenfunctions, where the coefficients are denoted by z hat sub n, and satisfy these ODEs. Now, as you can see here, we use a Leuenberger type observer. Okay, what about observer and controller gains? Well, in this approach, both gains are designed independently based on this first family of n naught modes and in advance. So for the case of the observer, if we consider this diagonal matrix and these two vectors, note that the coefficients c sub n are just the evaluations of the eigenfunctions at 0. Since these coefficients are not 0, the pair A naught C naught is observable, and we choose the first n naught observer gains such that the following Lyapunov inequality holds for some positive definite matrix P naught. The rest of the observer gains, we choose them to be 0. Similarly for the controller, and here we need an assumption, if the coefficients B sub n are not 0 within this index range, what this means is the shape functions have a non-trivial component in the direction of the first n naught eigenfunctions, then if we consider this vector, the pair A naught B naught is controllable, and we choose the controller gains in a similar fashion, namely that this Lyapunov inequality holds with some positive definite matrix P sub C. Now, these matrices, A naught minus L naught C naught, and A naught plus B naught K naught will appear shortly in the closed loop system description. So now that we have our observer and controller gains, we propose an n naught dimensional controller that has the following form. So it depends on the first n naught coefficients of our n dimensional observer. Now, for a closed loop system description, we also need to introduce an estimation error. So the estimation error is given as the difference between the true projection coefficients and the observer coefficients within this index range. And when we introduce this notation and we write out the ordinary differential equation satisfied by the estimation error, we see that it can be presented as follows. In particular, what is important here is that this innovation term that we had previously can be presented or decomposed into two parts. So we have one part here that depends on the estimation error, and we have another residual term, which we will denote throughout the talk by zeta, and is given explicitly here. Now we need to vectorize our ODEs to obtain a closed loop system description. So we will introduce some notations. For example, En naught is the first n naught of the estimation error. Similarly, we have the next n minus n naught modes of the estimation error, and the same for the observer. We also have some vectors and matrices, which all lead us to the following closed loop system description for t greater or equal to 0. Now, what we see here is that unlike, I should say, the case of state feedback, for the case of an observer-based control, we have a spillover phenomenon, meaning that we have coupling between the finite dimensional part and the infinite dimensional parts of the system. So X here is the finite dimensional part. So it corresponds to the observer modes and the estimation error modes. And we also have these tail ODEs. And we see that zeta which I reminded you depended on the tail terms appearing in the first equation, whereas x appears in the tail of these. So this is the spillover or the coupling phenomena that happens here. And as I've mentioned previously, the matrices that we've discussed, A naught plus B naught K naught and A naught minus L naught C naught, appear on the diagonal of the system matrix F. Okay, great. So we have a closed loop system description. What we also need is some way to compensate for this zeta term. So in this particular case, it can be shown that zeta squared can be upper bounded by this series. Now, note the appearance of lambda sub n here. This upper bound will, in a sense, force us to consider H1 stability of the closed loop system to be able to utilize this compensation of zeta squared. And indeed, we consider H1 stability of the closed loop system using the following Lyapunov function. Now, when we take this function and we differentiate it along the solution to the closed loop system, we obtain, first of all, again, a coupling term for zeta in the finite dimensional part. And as we've seen in the infinite dimensional part, in the tail ODEs, we obtain coupling of the finite dimensional part and the tail modes. So to deal with this coupling, we apply Young's inequality or the Cauchy-Schwarz inequality to the cross terms, which allows us to separate the tail modes from the finite dimensional part. And then when we sum all the terms together, we will get a series term, a tail term, which will allow us to obtain a quadratic term, negative term, in zeta squared to appear shortly in our LMIs. Summarizing, if we take eta to be this vector, our stability analysis gives us the following estimate, provided this matrix phi appearing here is negative definite. Again, this is not an LMI because we have this inverse term in alpha, but this can be easily converted to an LMI by just taking the Schur complement of this coordinate. So a few kind of key observations are in order here. First of all, this is not just one LMI. We still have the observer dimension, capital N, free. This is actually a sequence of LMIs, a sequence of semi-definite programming problems. And this means that this matrix P here that appears in the LMI can grow, in theory, its norm can grow very rapidly, thereby leading to instability for all capital N. Now, this has been a very, let's say, common criticism of LMI-based methods in the sense that, okay, we derive sufficient conditions, but can we say something about feasibility guarantees? Well, in this case, aside from deriving our LMI conditions, which is our first contribution, we also give a proof that these LMI conditions will be feasible provided capital N is large enough. And to come up with this proof, we actually had to use various tools from asymptotic perturbation analysis to essentially bound the norm of this matrix P in a very, let's say, delicate way, and then show that the rest of the decision variables in this optimization problem can be chosen in such a way which guarantees feasibility for large enough capital N. So if we summarize this, given this decay rate delta, if there exists a matrix P and a scalar alpha, such that the presented LMI holds, we obtain the following upper bound on the H1 norm of both the solution and the estimation error. And moreover, we have the theoretical guarantees, namely that the LMI is always feasible, provided capital N is large enough. Okay, so in this same paper, we've also treated several other cases. For example, when we have both operators bounded, namely non-local measurement and non-local actuation, we consider the case of L2 and H1 stability. And an interesting case was the case of Dirichlet actuation and non-local measurement. So again, we have, in this case, a bounded measurement operator, but an unbounded control operator. In this case, at that point in time, we were only able to show a much weaker exponential stability result, namely h to the minus half stability, using a Lyapunov function that had this form. And the reason for the problems that we had back then was that in this particular case, these coefficients b sub n grow linearly with n. And when you try to compensate in this regime, in the Lyapunov analysis, the cross terms, you will have a problem, even for the case of the L2 norm stability. So an immediate question in continuation of this work was, okay, what can we do for boundary actuation, or even more important, what can we do for boundary measurement and boundary actuation? And the first paper where we were able to deal with the unbounded operators was in these CDC and TAC papers, where we considered the Kuramoto-Sivashinsky equation. To be more precise, this is the linear Kuramoto-Sivashinsky equation. I'll hopefully get back to the to the semilinear PDE later in the talk. So what we see here is that we consider, first of all, mixed Dirichlet boundary conditions, meaning that the conditions are given in terms of the function and its second derivative. And we consider unbounded operators. So we have a boundary actuation and a point measurement in some point that I denote by x star within the interval. The first step here was to use dynamic extension. So essentially a change of variables given here that has the effect of moving the function u from the boundary into the right-hand side of the PDE, as we'll see in a second. But more importantly, as I've mentioned before, we had problem with the growth of these coefficients b sub n. This change of variables has a sort of smoothing effect. It will give a much better behaved sequence b sub n, which will allow us to get convergence in stronger norms. Now, just to mention a few existing results on KSC, that are given here, in most of them, the authors consider different boundary conditions, either Dirichlet or Neumann. What this leads to is to the fact that there are no explicit estimates, or even, let's say, closed forms for the eigenvalues and eigenfunctions. Now, if one wants to apply our approach in this particular case, the implication is that it's still theoretically possible, but will require computational approximations of the eigenvalues and the eigenfunctions. So going back to our problem, so we have this change of variables, this dynamic extension. Once we do it, we obtain an equivalent ODE PDE system given here with homogeneous boundary conditions and an initial condition of u at 0 equals 0. Similarly, we rewrite the measurements in terms of W and U. However, there's a price to pay when we do this change of variables. And this is the question of how are we going to treat this function U. So in this work, we treat U as an additional state variable, whereas its derivative, V, is the new control input. Namely that the price to pay for performing a dynamic extension is that now we are working with a PI controller instead of a P controller. And obviously, given V, U can be just computed by integrating its differential equation. Now, for the particular problem that I'm describing here, we use modal decomposition using Sturm-Liouville operator, and we have the following eigenvalues and eigenfunctions. Then we, again, represent the solution of the PDE as a series in this eigenbasis, and we derive the ODE satisfied by these projection coefficients. And the take-home message here is that when you go through the computations, you indeed obtain that Bn have this form. So in particular, this is an L2 sequence of non-zero elements. This is, again, the smoothing effect that I've mentioned that dynamic extension gives us for these coefficients. Now, I will not go into the analysis here. It's very similar to what I presented in the previous slides. I'll just say that we again carry out H1 stability analysis and obtain two linear matrix inequalities with some positive definite matrix P and scalars alpha and beta. And their feasibility, again, give us H1's exponential stability of the closed loop system with decay rate delta. And again, we have theoretical guarantees. Namely, these LMIs will always be feasible, provided capital N is large enough. So in the same paper, we also consider the case of L2 gain and ISS analysis. So what we have here is, again, the linear Casey equation, where we now introduce two disturbances. So we have a distributed disturbances, denoted by D, in the right-hand side of the PDE. And we have another measurement disturbances that I denote by sigma appearing in Y. The disturbances satisfy these smoothness conditions. Again, we carry out dynamic extension given here. But in this case of L2 gain and ISS analysis, we fix three parameters, a positive gamma and rho W, rho U, and we introduce the following performance index. Our goal in this part was to find conditions that guarantee that along the closed loop solution, the solution to the closed loop system, the following inequality holds, where V is again this nominal Lyapunov function that we had previously, and W is given here. Now, what is important here is that if we can guarantee it, we immediately obtain two results. For the case of delta equals 0, we will get the fact that this performance index is non-positive, meaning that we carried out L2 gain analysis. And for the case of positive delta and rho W equals rho U equals 0, we get an ISS result, namely that for some positive constant, the following inequality holds. However, when we carried out the L2 gain analysis, we initially encountered a problem. So we again arrived at the following LMI. However, when we tried to apply the same tools that I described earlier to show feasibility, we had some difficulties at first. And the novelty in this paper came indeed in the proof of the LMI feasibility for large enough gamma and capital N. And the reason for the difficulties that we had was the appearance of this matrix C here. So this matrix C is a positive term that is not multiplied by a decision variable and does not decay with capital N. You can think of it as something that remains constant no matter how I play with the decision variables and with capital N. You can compare it, for example, with this term here. And we actually had to come up with a different proof to show that this LMI is feasible for large enough gamma and capital N. Also, for the case of ISS with distributed disturbance equal to 0, we've managed to get another type of theoretical guarantee, namely that if the LMIs are feasible for some capital N, they will always be feasible for N plus 1. And this gives a certain structure to these semi-definite programming problems in the sense that if we increase capital N, the performance of this, the closed loop system does not deteriorate, which is an important guarantee to have. Okay, so what I presented so far was our approach, and inevitably the endpoint of our approach was linear matrix inequalities, right? So we wanted some LMI or LMIs to be feasible, and this guaranteed the desired stability or ISS result or L2 gain result of the closed loop system. Now, when you go to the literature on semi-definite programming problems, you see two recurring themes. First of all, such problems for implementation purposes would like the problem to be sparse. And second, such algorithms have problems when the dimension of the LMIs is very large. And this is indeed something that we saw in the numerical examples. So in this ECC paper and Automatica papers, we tried to tackle this problem. We asked ourselves, well, can we make the computations or the verification of feasibility more efficient? So, for example, consider the following heat equation with Neumann actuation. In this work, we considered non-local measurement. And For non-local measurement and L2 stability, we do not need a dynamic extension. So we just have the following eigenvalues and eigenfunctions. Again, we derive the ODEs satisfied by the projection coefficients. These are given here. Note that Bn is, let's say, an okay sequence in the sense that it's an L infinity sequence. It does not grow with n. And also because we're working with non-local measurement, the upper bound on zeta changes slightly and is given here, where C is the kernel given in the non-local measurement. Now, the big difference in this work came in the closed loop system description. Namely, we consider a reduced order closed loop system. So a very similar structure to what we had previously, except for the important fact that this finite dimensional part contains only the first n naught plus 1 modes of the observer and the estimation error. And this is the system matrix here. So what we essentially do is that we have an intermediate layer of modes, which we denote by z hat n minus n naught and en minus n naught, that we completely ignore in this closed loop system description. And why can we do that? Well, if you go to the ODE satisfied by these components, you immediately see the following fact. First of all, en minus n naught is exponentially decaying because this matrix is Wolbitz. And this component will be exponentially decaying, provided we show exponential stability of the reduced order closed loop system. Namely that if we show the desired stability result here, these components sort of take care of themselves. And this is a very simple realization, but has very important implications and advantages. First of all, what you can see here is the fast-slow structure of the dynamic explicitly shown. We have a slow part corresponding to the finite dimensional part, and we have the fast-tail dynamics, which is a more correct mathematical way to describe the closed loop system. Also, our stability analysis in this case results in reduced order LMIs. We'll see them in a second, but the key point is that they do not grow with the observer dimension capital N. Thereby, we get something that is much more computationally efficient. And an added bonus, or a very important feature, is that it trivializes many of the proofs that of theoretical guarantees that I've mentioned earlier. In particular, for example, feasibility for a large enough n, or the fact that feasibility for n gives feasibility for n plus 1 can be seen in a much more explicit way when we write the closed loop system in this way. So for L2 stability analysis, we use the following Lyapunov function. Now note here that we include this en minus n naught. However, we've already mentioned that it's exponentially decaying. So when we carry out our stability analysis and we take this PE to infinity, we obtain reduced order LMI, which is given here. Again, its dimension will not grow with capital N. And indeed, when we carried out the numerical example for this project, we saw that we are able to verify feasibility for even capital N, let's say 30, whereas for the full order closed loop system description, we were able to maybe get n equals 9 or n equals 10. Also, I'd like to to mention two points. So in this case, we do not use dynamic extension, so we can treat in this model, general time varying delays and sample data control. And also in this paper, which is under review in Automatica, we also consider the case of delay compensation and more specifically compensating a constant part of an input delay. And for the first time, we used a classical predictor in combination with a finite dimensional observer-based control. So what about delayed implementation? Okay, so consider the following model that we have in our 21 Automatica paper with the following ingredients. So a very similar model to what I've shown in the continuous time with the following differences. First of all, we have a known measurement delay, which is upper bounded by some constant tau n. And we have an input delay that is unknown. Again, this will be crucial. We will not, when we design our observer, we will not have access to tau u. Now, the framework that we presented this paper can be used with either C1 delays or sawtooth delays, which are correspond to sample data or network control. Again, we derive the ODE satisfied by the projection coefficients, and you can see that the delay is introduced into the right-hand side of the ODEs. Again, let n naught, the controller dimension, be such that this inequality holds, and capital N be the observer dimension. Now, I would like to point out that I'm using a different notation here. So instead of minus delta, we have minus delta sub tau. This will be important in a couple of slides, and I'll get back to this point shortly. So this is the form of our finite dimensional observer, and the coefficients satisfy these ODEs. I remind you, tau u, the input delay, is not known, so we cannot use it in the observer ODEs. Instead, we use u of t. The controller it has a very similar form to what we saw earlier, and the closed loop system that we obtain in this case is given here. Now we can see that the delays appear on the right-hand side. Moreover, they can be separated into, let's say, two categories. First, we have both tau u and tau y appearing in the finite dimensional part, here, here, and here. But what will be more important to our discussion in a slide or two is that we have the measurement delay appearing in zeta. And I remind you that zeta needs to be compensated in our stability analysis using such bounds. So the compensation of these delays is a challenge that we need to tackle if we want to carry out stability analysis of the closed loop system. So we use a Lyapunov function for H1 stability that has this form. So we have, again, the nominal Lyapunov function that we've already seen, and augmenting terms, VSI and VRI, that compensate the delays in the finite dimensional part. However, when we carried out the analysis using this Lyapunov function, we saw that it doesn't go through. And the reason is that the analysis does not allow to compensate for zeta at time t minus tau y. So in order to do that, we have to use Halanay's inequality that I'll present here. So Halanay's inequality says the following. If we have delta 1 less than delta 0, and we have v, an absolutely continuous function, satisfying this inequality, then it decays exponentially, where the decay rate is this delta tau that I remind you we saw when we chose the controller dimension. So what we see here is a trade-off. On the one hand, I have an inequality that gives me access to past values, history values of the Lyapunov function v. On the other hand, there's a price to pay in the decay rate. So the decay rate delta tau here is smaller than delta 0. When we use Halanay's inequality in our case, we obtain that this additional past or term that uses past values can be upper bounded by two ingredients. And one of them is exactly this negative quadratic term that we were seeking for zeta. Again, in this context, we prove that the resulting LMIs are always feasible for large enough observer dimension capital N and small enough bound on the delays that I denoted by tau sub n. Okay, so the results for delayed implementation that I've discussed now are in the realm of, let's say, robustness, okay? But this immediately leads to the following question. Okay, what about large delay compensation? Can we do something when the delay doesn't tend to 0? And the answer is yes. In this LTSS paper, we consider the following heat equation, where we have, again, Neumann actuation with a known large delay R appearing in the control input, and we have non-local measurement. The challenge in this paper was observer-based L2 stabilization, but this time with an arbitrarily large R. And again, a recurring theme, we want LMI conditions that are efficient, that have theoretical guarantees, and can be easily implemented. So we do this in two ways. The first approach that we used was subpredictors or sequential predictors. So we use a chain of M subpredictors where the arrow notation here essentially means predicting. For example, this component at time t predicts the future value of z and naught, the first n plus naught plus 1 modes of the state, but at time t plus r divided by n. Now, when you go through what this prediction means, you'll get that the first subpredictor at time t will predict or approximate the future value at time t plus r of z and naught. And when we use this guy for the proposed controller, we will get that u at time t minus r is approximating what we really want, right? Which is the controller for the, let's say, state feedback case. So the novelty in this project was the following closed loop system description. And it has a lot in it, but the take-home message here is the following. First of all, note that we write the closed loop system in different terms. We have z and naught, not the observer modes, but the state modes in the first line. We have the subpredictor estimation errors, and we have the tail ODs. Moreover, the usefulness of subpredictors gives us the following. First of all, it completely eliminates the delay from the first and the third ODs. Secondly, instead of having a delay equal to r in the estimation error ODs, we have a delay given by r divided by n. Now, the price to pay, of course, is that the dimension of the estimation error can be large because we take m to be large. So in this case, we again obtain a reduced order closed loop system, and we carry out our L2 stability analysis to obtain reduced order LMIs. However, we still have the same problem, okay? So we derived LMI conditions that guarantee L2 stability of the closed loop system, but can we say something about their feasibility when R is arbitrarily large? And the reason why this problem is non-trivial is, again, because we're working with observer-based control. So we have coupling between the finite and the infinite dimensional parts. So another contribution in this paper is to give a theoretical proof that indeed these LMIs will be feasible for any R if we take the number of subpredictors and the observer dimension to be large enough. And just to kind of give a sense of why this is non-trivial, I'll briefly describe the steps that we use here. So in the first stage, we fix our number of subpredictors, capital M, by considering only the ODEs of the less subpredictor error. At the second stage, having this M fixed, we construct a Lyapunov function only for the subpredictor errors by induction when we take into account the natural cascaded structure of these ODs. And only then can we choose the remaining decision variables in an explicit way, which depends on n, and take n to infinity to show that indeed this optimization problem will be feasible provided capital N and M are large enough. So if you're interested, the proof is in the paper, but I want to stress again that it is highly non-trivial. A second method that we consider here is compensation of R using a classical predictor that is given here. Note that on the right-hand side, we have the first n naught plus 1 modes of the observer. The resulting closed loop, reduced order closed loop system, in this case, will be expressed in terms of the predictor, the estimation error, and the tail ODEs. Again, our L2 stability analysis gives us reduced order LMIs. And also for the case of the classical predictor, we have theoretical guarantees. The LMIs will be feasible when R can be arbitrarily large, provided the observer dimension is large enough. So this is indeed for the context of PDEs, the first time that such guarantees have been derived, to the best of our knowledge. Okay, so what about sample data implementation? So in this Automatica paper, we considered the following heat equation. And the main question that we asked ourselves was, okay, can we extend our approach to sample data control? So here we will consider this PDE in the presence of two independent communication networks. So on the measurement side, we will have sampling instances that I'll denote by S sub j, such that the sampling interval is upper bounded as follows. And we will also introduce a quantizer, a function q from R to R satisfying this inequality where capital delta is the quantization error bound. Then, having these definitions, we will consider discrete time in domain point measurement of the following form. And just to mention, in this work, we consider H1 ISS analysis of the closed loop system. So sometimes in the literature, or often it is common to consider a quantization together with saturation. I just want to mention that in our framework and using our methods, we can do that. But in this particular paper, we decided only to focus on quantization. Similarly, on the actuator side, we introduce the following controller hold times that are upper bounded again as follows. And the novelty here is that U, the control input, is generated by a generalized hold device, meaning that it satisfies the following ODEs. And by generalized hold, we mean the following. Given VTJ on this interval, U is computed just by integrating this differential equation or just doing out this linear interpolation. So we can see the block diagram of our system here. Again, we carry out dynamic extension given here, and we obtain the following equivalent ODE-PD system with homogeneous boundary conditions, and we rewrite the measurement as follows. The N0 plus 1 dimensional observer-based controller is given here, where remind you that U is an additional state variable, and we write out a reduced order closed loop system. Again, it has many components, but I just want to point out what is important. First of all, we have a delay, tau sub y, that is induced by our sample data. And naturally, we introduce the quantization errors, sigma sub u and sigma sub y, that appear on the right-hand side. In our analysis, we will treat them as disturbances whose L infinity norm is upper bounded by the quantization error bound delta. So for H1 ISS analysis, we wanted in this work to use Wirtinger-based Lyapunov functionals. Why? Because in the case of finite-dimensional systems, they were shown to be extremely efficient for sample data control. However, when we tried to do that, we stumbled on a problem. So when you go to the literature and you want to apply Halanay's inequality, let's say on this interval, S sub k plus 1, all of the formulations that we found required continuity of the Lyapunov function on this interval. However, in our case, we have two sampling sequences that are independent. So V may jump at times T sub j within this interval. It can have the following behavior. And we couldn't find a Halanay's formulation that accounted for such or allowed for such a behavior. So instead, we had to prove a novel version of Halanay's inequality for ISS. So there's a lot here. I'll just point out the key ingredients. First of all, we see a very similar condition to what we've seen in the previous formulation of Halanay's inequality, but we add a constant d here, right? This d will be in our model the quantization error. Also, when we consider the interval AB, we allow V to have a finitely many points where it exhibits a jump discontinuity, provided it does not grow in the jumps. So if V satisfies these conditions, then we can show that it can be upper bounded on the interval using two components. The first one is what we expect from the previous formulation, and also another integral term involving this term D appearing on the right-hand side. So when we have this Halanay's inequality for ISS in hand, we again obtain reduced order LMIs, but for ISS this time. And their feasibility guarantees the following estimate on the solution of the closed loop system. In particular, we see on the right-hand side the quantization error appearing, and we also have a multiplying factor that I denote by R. And again, the recurring theme, R can be explicitly estimated in our analysis. So once the problem is feasible, you have the decision variables, you can compute and obtain this R explicitly. As for theoretical guarantees, the LMIs are always feasible for large enough capital N, small enough sampling intervals, and their feasibility for N implies feasibility for N+1. So the last section is semilinear PDEs, but we're running short on time. So I'll just mention briefly that we have some results on semilinear PDEs. The natural question is, can this approach be generalized to nonlinear equations? We were very much motivated by this paper by Kalafilis, which designed control Lyapunov functions for global boundary L2 stabilization of semilinear parabolic PDEs, under the assumption that the semilinearity exhibits what he calls a linear growth bound. In a different paper that is under review, we also considered the case of state feedback stabilization of a semilinear heat equation with unknown or known semilinearity with a linear growth bound. I wanted to present results on regional stabilization of the Kuramoto-Sivashinsky equation, where we add the semilinear term. I think I'll stop here. I'll just say that our approach can be extended, and we have a paper in LCSS recently accepted that shows that we can extend our approach. I'll just skip to the result. So we obtain, again, an H1 stability result. However, we need also an estimate on the domain of attraction. And our analysis can give us such an estimate, again, in an explicit manner. Namely, we call it a lower bound rho. If the L2 norm, initially, the L2 norm of the derivative of Z is upper bounded by this rho, then the solution of our closed loop system exists for all time, and we have this H1 exponential stability result. So I apologize if this was too fast. I'll be happy to answer any questions about it. So just to conclude, we had a dream when we started about efficient finite-dimensional observer-based control, and it's becoming true. So we have an LMI-based method for parabolic PDEs via modal decomposition. All quantities of interest, observer dimension, the ISS and L to gain, the delay bounds, can be obtained from LMIs. We have all the accompanying theoretical guarantees. The LMIs are proved to be asymptotically feasible, and important to state, and I haven't shown it here, in examples, they're only slightly conservative, at least for the non-delayed case. The LMIs are constructive. They can be verified by any user without even any background in PDEs. We showed that we can compensate for large input delays by using subpredictors and classical predictors. For point measurement and actuation via dynamic extension, we presented a sample data implementation using a novel generalized whole device. And I briefly mentioned this, but didn't go into detail. Our approach can be extended to semilinear parabolic PDEs. So if someone is interested, this is my website where the entire publication list can be found, and I'll be happy to discuss it. Just a quick advertisement before I'm done. So tomorrow, Emilia is giving a talk on using delays for control in the TDS seminar, if someone is interested. Thank you very much for your attention, and I'm ready for questions.